everybody. It's a pleasure for me to be here at Quantum to Business Europe. So thank you very much for the invitation. My name is Davide Corbelletto, and I've been working in computer science for almost 20 years, the last 8 of which in Intesa Sanpaolo group technology area, that basically is the ICT department of the bank. And I'm here to give you to share with you some insights about our journey towards quantum technologies and especially quantum computing. For those who maybe don't know us, Intesa Sanpaolo is the leading Italian bank in all the segments, and also the third European bank for market capitalization. And besides pursuing being an ethical bank, financial inclusion is also committed to provide its customer the best innovative technology solution. And that's why we have a quantum competence center within the bank. The competence center of the bank, which I have the honor to lead, has 5 main objectives. So, of course, enabling experimentation on quantum computing, training the future workforce we will need, hopefully, in a few years, in order to develop at scale quantum computing and operationalize the various POC we have developed so far. We also provide qualified advisory to other departments of the bank. For example, our venture capitalists that who started to invest in quantum computing in 2022, or for example, our cybersecurity colleagues are dealing with the potential threat that quantum computing poses to asymmetric cryptography. We are also trying to build an ecosystem around the bank, partnering with important university and other public and private institutions. And finally, we are also committed in defining guidelines to, let me say, enable a coherent and progressive adoption of this technology inside the company. But why a bank is interested in quantum computing? Of course, Filippo has already commented about that, but let me just recap which are the relevant group of use cases we are interested in delving into. So, starting from optimization, inside the bank, you do a lot of optimization every day. So, we know that quantum computers are particularly suitable to solve this kind of problem. Then there is stochastic modeling, and as Filippo mentioned before, you cannot say bank without saying Monte Carlo. So we know that Monte Carlo, in its classical formulation, has got some limitation. For example, limitation in convergences, because of course you are using basically pseudo-random number generator in order to create your random variable. And so you can have a problem of convergence of the model when the number of shots is particularly high. And in this field, quantum computer can be a game changer, of course. There's also room for improving machine learning, because not only in the speed of the algorithm, but also in the accuracy of their outcomes. So we are also trying to figure out how to use quantum computing to enhance machine learning algorithms. I will give you an example in a few minutes. And of course, as I mentioned before, there is cybersecurity. So banks can simply ignore quantum computing at the moment because there is a concrete threat to all the asymmetric cryptography protocol that we, for example, use to ensure the safeness of financial transactions. This is just a roadmap that depicts our journey towards quantum. Started in 2020 when we launched the Quantum Competence Center. Of course, I don't have time to comment every single box that corresponds to a relevant milestone we achieved in these 4 years, but I will concentrate just on a couple of latest results, in particular 2 peer-reviewed papers we published in 2023 with the contribution of IBM and Politecnico di Torino. The first one is very similar to Mosaic, if I may, Filippo, because it's a study on stochastic modeling. And so basically here the idea is to find a way to represent in the quantum realm what we can call our corporate credit risk framework credit risk analysis framework for corporates. And basically, the idea was to substitute Monte Carlo simulation using their quantum equivalent that is called quantum amplitude estimation. This is an algorithm that has 2 advantages if compared with the classical solution. The first one is that it scales quadratically in terms of time complexity. And so basically in the same time you can do more than you are limited today. And this could be a problem, especially if you are going maybe in the future to double the number of corporate you are trying to assess the risk of. And another thing that it is relevant, I already mentioned before, is the fact that we were able to prove, even in, of course, with a toy model, so with a small data set, but using real data, because I think on this particular point we agree. You have to use real data, of course, properly anonymized and masked, but it is important to rely not only on synthetic data, but on the data you have at your disposal. And so we were able basically to demonstrate the fact that we have let me say, a convergence of the model, even when the classical one, the classical counterparty, has some problem, especially when a threshold of shots is overcome. Then the second work I want to tell you about is, let me say, our first quantum machine learning work. It has also been presented at an international, really relevant international conference, the IEEE Quantum Week in September last year, and then was published by IEEE in November 2023. And it's about an unsupervised clustering technique, principal component analysis, which is really, let me say, and highly used in lots of financial workloads, especially as a preprocessor in order to reduce the dimensionality of the problem. Just to give you an example that is exactly, let me say, the topic of the paper, given a very big matrix, imagine a matrix of correlation between, for example, interest rates of market rates. The idea is to have an algorithm that is able to prune this matrix in order to, of course, erase all the spurious correlation, but also to filter the correlation in order to focus only on the strongest one that are, of course, the most relevant. And this thing can be really computationally expensive sometime. And so we are trying to, with this work, we have tried to figure out a way in order to cope with with a higher dimensionality of the problem. And so we started basically from a work that was published in 2018 by China Northwest University, where they theoretically claimed claimed the fact that the procedure they have conceived was has got an exponential speed up in terms of type complexity. The problem is that they weren't able to practically verify this because there were two big problems that we were able to overcome with this work. The first one is that their approach was limited just to integer eigenvalues, and so we extend their work and now we are able to cope also with the real eigenvalues that are exactly what you need in a practical use case, in a real world scenario. And the other things is that they assume that it would be possible to extract eigenvectors, because you don't need only the value, but you also need the sign when you do principal component analysis, so the direction, basically. And we were able, with a procedure that is called state tomography, we are also trying now to publish a package in Qiskit that is going to do this. So it's the code is now under review in order to extract eigenvectors. And so, given these two things that basically overcome the limitation, we were able to demonstrate practically, of course, again, with a toy model, with a restricted number of data, due to the limitation of data encoding that quantum computer, of course, continue to have at the present moment, we were able to verify practically the exponential advantage of this procedure. Well, I've talked about what we have done so far, but now let's see, let me say, a preview of what we are doing and what we are going to do in the near-term future. So in February, we released two preprint version, in preprint stage, two new papers, one with Classic and Politecnico di Torino about option pricing. And I think, of course, we have verified, so I don't know if there is any other paper that has recently been released on arXiv. So I'm not sure 100%, but 1 month ago it was the first paper that tried to cope with actual let me say, with options that are not plain vanilla, but with rainbow options, so with more than one underlying asset. Then there is another work that is a novel approach to portfolio optimization that try to, and this was developed with the help of Data Reply. The idea here is to not use the classical Markowitz solver that basically try to maximize the return while minimize the volatility with a linear, let me say, linear formulation. But we are trying here to maximize the Sharpe ratio. So the problem is quadratic by itself, so it's difficult to translate in a Kubo formulation. And here we are using, of course, analog computing. Then we continue our collaboration with IBM, involving this year also the Central Bank of Italy and University of Verona, in a work that is trying to use quantum computing to avoid gridlocks in security transaction settlement system. Then we have of course, Intesa Sanpaolo is part of the National Center of Research in High-Performance Computing, Big Data, and Quantum Computing. And so we were able to launched 2 innovation grants. So we were granted basically to work on 2 projects financed by Next Generation Europe, what program that is also called in Italy the National Plan for Resilience and Recovery. And with these funds, with lots of academic partners, for example, Politecnico di Milano, Università of Padova, Università La Sapienza in Rome, we have just started these 2 brand new projects on fraud detection and credit scoring. And last but not least, I'm really happy to announce that we are finalizing let me say, a new collaboration with Links Foundation and Quera about default prediction using neutral atom technology. And that completes my talk, so thank you very much for listening.
Thank you so much, Davide.
I have also the slide for the Q&A. So.
Yeah. Questions?
So thanks for the presentation. In Banca Intesa, you have a very ambitious, let's say, roadmap about possible applications of quantum computing in the finance sectors. So you told us the projects that you have already running. I'm curious to know your personal opinion about what could be next. If you have any ideas or what do you like to work on?
I think there are, let me say, of course, some of the use cases that were named on the slides, we have already maybe started internally a proof of concept. At the moment, one thing is really relevant. I know it's kind of awkward to say in a world of digital payment, but one problem that now we are trying to solve, and at the moment we are just using emulators, so basically high-performance computing system in order to emulate a quantum computer. So we don't have at the moment executed the prototype on any kind of machine, is about cash flow optimization. So basically the recharge of the automatic teller machine. So it's awkward because it's a word in which we are trying to pursue, you know, the digital payment, but we have also to cope with customers that needs to, you know, to have cash, no? And this is a really difficult problem if you basically consider also this kind of constraint, the fact that now automatic teller machine can be also recharged by, for example, by retailers at the end of the day when they are going to put money in the automatic teller machine. And so you have to consider this, and it would be really, let me say, a good business case to save a lot of money, because of course the companies that ensure the fact that the cash is safely delivered to the automatic teller machine, especially after COVID, are costing, the cost of these companies is really high. So it's important to find a way to cope with this problem. And the classical solution we have used so far, it's not very efficient. So we are trying to, with let me say, quantum inspired and also hybrid quantum, we are trying to enhance let me say, the quality of the solution.
Thank you.
Thank you very much.
Yes, we have 1 minute for a question.
A fast one. You said, why don't you use real quantum machine? It's fun. They are powerful.
No, we are using, for example, for for the two papers I've presented before, we have used in pay-per-use mode the real quantum backend up to 127 qubit Eagle system. Even if I have to confess that the best results at the moment we gained using the Falcon system, so the 27 qubit, because it's more stable. So of course you cannot encode too much data, but it's more stable. So we have also have some experience with ion traps. Now we are starting also neutral atoms. I think the only technology we missed at the moment is photonic.